Warahmatullahi wabarakatuh. Today we are going to present about stability of control loops and also tune feedback controller. So we have online controller tuning. In online controller tuning, we need to have online controller tuning because usually during designing control system, we have set a preliminary controller settings based on process knowledge, control objectives and prior experience. So after a controller is installed, usually the preliminary settings are often satisfactory, so we don't need to set it anymore. But for critical control loops, the preliminary settings have to be adjusted in order to achieve satisfactory control. So this on-site adjustment is also known as online tuning or field tuning or controller tuning. So online controller tuning usually involves plant testing, often on a trial and error basis. The tuning can be quite tedious and time consuming. So one of the ways is introduced by Ziegler and Nichols. So Ziegler and Nichols introduced a trial and error procedure. First, we have to set tau d into 0 and also tau 1 into the largest possible value. And then next we have to set the KC equal to a small value, for example like 0.5, and place the controller in the automatic mode. And then next we have to introduce a small momentary set point change so that the control variable moves away from the set point. Gradually increase KC in small increments until continuous cycling occurs. So the term continuous cycling refers to a sustained oscillation with a constant amplitude. Continuous cycling is like when the graph has a sustained oscillation with a constant amplitude, meaning the amplitude is almost the same. So that is continuous cycling. The numerical value of KC that produces continuous cycling is called the ultimate gain, KCU. And also the sustained oscillation is called the ultimate period, PU. So next, we have to calculate the PID controller settings using the Ziegler-Nichols tuning relation in the table 11.4 below. Here is the table. As you can see, we can refer to this table for calculating the PID controller setting. So we have to evaluate the Ziegler-Nichols controller settings by introducing a small set point change and observe the closed loop response. Fine-tune the settings if it is necessary. So for the response, everyone can refer to the graphs next to this table 11.4. For the response, we have KC less than KCU is over them. Everyone can see the graph how is the response would be depicted. For KC equals to KCU, continuous cycling occur. Everyone can see that the amplitude is the same. General stability criterion. So most industrial processes are stable without feedback control. Thus, they are said to be open loop stable, or also known as self-regulating. An open loop stable process will return to original steady state after a transient disturbance. So by contrast, there is an unstable process as well, which is exothermic chemical reactors. It is known as open loop unstable. So this process are extremely difficult to operate without feedback control, since it is hard to be controlled. So The definition of stability is an unconstrained linear system is said to be stable if the output response is bounded for all bounded inputs. So it has to be bounded. If it is not bounded, it is said to be unstable. So what is meant by bounded input? Bounded input is an input variable that stays within the upper and lower limits for all values of time. For example, if we have a variable of u bracket t that varies with time, if the u is a step or sinusoidal function, then it is bounded. Next is the characteristic equation. So as you guys can see, there is a GOL here. The GOL is actually an open loop transfer function. It is equals to GC times GV times GP times GM. GOL is actually a ratio of polynomials in S, a rational function. 1 plus GOL equals to 0 is the characteristic equation of a closed loop system. So looking at the definition of the general stability criterion, it is the feedback control system is stable if and only if all roots of the characteristic equation, this 1 plus GOL, are negative or have negative real parts. If it's positive, the system is unstable. So there is also a graphical interpretation of this stability criterion. So everyone can check out the graphical interpretation for a better understanding. So if a system that has all negative real roots, it will have a stable non-oscillatory response. If you see at this table, non-oscillatory response is overdamped with a value of Kc of moderate or large. On the other hand, if one of the real roots is positive, then the response is unbounded, which is unstable as the definition of stability that I have explained earlier. So when it is unbounded, it results in oscillatory response. If we refer to this table, it has a value of Kc which is small. So if the complex roots have negative real parts, the system is stable. Otherwise, it is unstable. That's all from me. Thank you.
Okay, next we would like to see about the first order plus time delay model. Okay, so there will be a tree response right here, which is overdamped, continuous cycling occur and unstable. So when the Kc is lower than Kcu, then we will recognize it as a overdamped. Then if the Kc is equal to Kcu, it is a continuous cycling occur. And then if the Kc is larger than Kcu, it will be the unstable. And then this is for the equation. This is the equation for the first order plus time delay model, which is the GS is equal to Ke power of negative degree S. Okay, this is the equation for the first order plus time delay model. Okay, moving next to the Cohen method. The figure 1, which is we will estimating of the parameter of the first order plus that time process model. And this is the equation. The tau m equals to 3 over 2 multiplied by the t2 minus t1, where t1 is the time at which delta c is equal to 0.283 times with delta cs. And another one is time at which delta c is equal to 0.632 times with delta cs, and c, which is the planned output. So we can see that at table 8 is the Cohen controller setting. We had 4 type of controller type, which is P, PI, PD, and PID. And this is the list of the KC, tau 1 and tau D. You can refer this table. Okay, and then lastly, for the root stability criteria. Okay, the definition is a necessary and sufficient condition for all roots of the characteristic equation to have negative real part is that all the elements in the left column of the root array are positive. Okay, so the characteristic equation for root stability criteria, we can see that only for polynomial in S, an s power of n plus this, then till we get this, right? This here. Okay, so how we gonna test it? So for the first test, we should identify if any of the coefficient is negative, there is one root positive. If the order or coefficient is missing or 0, so we will consider this process is unstable. No further analysis is needed. Okay, so this is the construct root array in this table. Okay, and then formula that calculate the remaining part, which is the B1, B2, C1 and C2. Okay, so that's all from our group 9. Thank you.
Assalamualaikum warahmatullahi